This is the first lecture for Module 2 where we talk about finite state machines. There will be 2 lectures recorded in this module. So, finite state machines, this comes under the topic of models of computation. Models of computation are just what you would think. They are mathematical models of how computation occurs, and we'll talk about several different models of computation throughout the semester and how they relate to real-world programming languages. As usual, here are the outcomes. Check and see that you can do these things at the end of the modules to make sure that you understand the material. Okay, so finite state machines. Why do we talk about these things? There's 2 reasons. One is they have theoretical value, and one is they have actual practical value. So, what is the theoretical value? Well, what's the core question of computer science? The core question of computer science is, what can a computer compute? What can a computer do? What can an autonomous, mindless system do? And to answer that, we need some kind of a formal model of what computation is and how computation is performed. And so we ask ourselves, okay, what is computation? Well, if you get back to the very basics again, just like we did with language, computation is nothing more than the mindless manipulation of symbols using some formal rules. Now, what do I mean by formal? There's no judgment, there's no opinion, there's no ambiguity. You literally have one possibility. Once you choose to do an operation, you literally have one possibility as to how that operation will be performed. They have to be mindless. Computers perform computation. Computers are the essence of mindlessness, right? A computer in one hand, box of hammers in the other, you have an equal amount of intelligence there. And it's about the manipulation of symbols. So remember what we talk about with formal systems, a small number of things, a small number of operators to modify those things or rewrite those things or manipulate those things. That's what a computational system is. So if you think about it, just go back to basic addition. 1 plus 1 is 2. How do you know that? First of all, forget meaning. You have embedded the meaning that 1 plus 1 is 2 has the meaning of there is one of something and another one of something, and you put them together and you have 2 of those things. That's great, but that is an application of the computation, just like when we said communication was an application of the language, or programming is an application of the language. It's not what the language is. Addition is a application of computation. When we go back to this mindlessness in terms of computation, it helps because we can allow computation to occur with any kind of symbol rewriting. So now it applies to word processing, language manipulation, mathematics and numerical things, right? Things that we apply meaning to. Those are the applications. So we have many different models of computation out there. They're all coming to the same conclusion, by the way, which we'll get to too. A finite state machine is one of the many models of computation, and we introduce it here because it's actually a very weak model. It can't do as much as other models of computation. You probably have heard the term Turing machine. What is a Turing machine? It's a mathematical model of a computation, specifically a mathematical model of how a computer would do computation. Turing machines have memory. Finite state machines don't. So a finite state machine can't do all computation. Turing machine can. They're very weak. So this is the theoretical value. What can a computer compute kind of discussion. What about practical value? Well, it turns out finite state machines are used everywhere. Now, if you think about the term finite state machine, what does it mean? It means you have some kind of a machine that has state, and it has a finite number of states. Well, you're surrounded by these things. Your television has state, on, off, volume, channel setting. Aircraft have state, at gate, taxiing, wheels up, wheels down. Your car has state. Usually non-player characters in a video game are based off of state machines. They're getting smarter, right? They're getting some AI type stuff in there, machine learning type stuff in there, but guess what? There are machine learning systems that are built on state machines. So we're going to consider the theoretical aspects more so in this class, and we'll get to the practical aspects. The theoretical aspect that we're going to consider a finite state machine is, since we're talking about formal languages, as language recognizers. We'll say, we've already discussed what a language is. We've already discussed what a grammar is. So we can say, okay, a language is a set of strings. A grammar is a set of production rules that produces those strings. Now we're going to say a finite state machine is a mathematical device that will recognize those strings. And when they recognize those strings, we say that the finite state machine accepts it. So if you have a finite state machine, you feed it a string as input. If that string is in the language that the finite state machine represents, the finite state machine will accept that string. And then if not, it will reject that string. Every language has its own finite state machine, and as you would suspect, there are an infinite number of finite state machines for each language, most of which are trivial. Okay, so let's review really quick. We know what a language is, right? A language is a set of strings. We know what a grammar is. A grammar is a set of rules by which a language is constructed, and we've specifically talked about the Backus-Naur form. And we know what the Chomsky hierarchy is, and we've discussed the Chomsky hierarchy in terms of characteristics of the grammars. Now let's talk about the Chomsky hierarchy in the context of models of computation. It turns out, and we'll discuss why this is true, the regular languages correspond directly to the model of computation called the finite state machine. By the way, when you're Googling, there is an alternative term for finite state machine. It's called a discrete finite automata. Authors use these words, I think, pretty much 50-50, and they're interchangeable. I like finite state machine. Discrete finite automata is also fine. Discrete referring to specific states. Finite, again, meaning finite. Automata, meaning it happens automatically. For reference, the context-free languages correspond to something called a stack machine, which is also called a push-down automata. Push-down meaning you're pushing things down a stack. Context-sensitive corresponds to a Turing machine, but with finite tape, and unrestricted refers to a Turing machine with infinite tape. Clearly, we cannot make, in practice, infinite memory. In all practicality, we have infinite memory, what with cloud services these days, but you cannot make a machine with literal infinite memory, so this is clearly a theoretical device. Okay, so we're going to stick with regular languages and finite state machines. When we transition to the context-free and stack machines, hopefully that transition will be very clear and simple for you. Okay, so again, it's a mathematical device by which we recognize languages. How do we recognize it? We feed a string into this machine, it processes the string, and when the string is completely processed, then this finite state machine will either accept that string or reject that string. Now, to match a particular language, the finite state machine must accept all strings in the language that it's designed for, and it must reject all strings that are outside the language it's designed for. And again, each language may have an infinite number of finite state machines, most of which are trivial, and corresponds to the regular languages. Okay, so what is this mysterious finite state machine? Let's start with a formal definition, and I'm going to end with the definitions of it in this lecture, but then we'll go through examples of finite state machines in the next. The examples clarify things greatly. Some people are intimidated by formal notation. You'll get over that, but the examples clarify things greatly because they're graphical, and we love graphical stuff as human beings. So formally, a finite state machine, M for machine, is actually a tuple. That's what we call these sequences of sets or sequences of things, is a tuple. It's a 5 tuple because there's 5 things. It has capital Q, the set Q, a finite set of states. Some authors use capital S, by the way. So don't be discouraged when you see something different. It's a finite set of states. That's why it's a finite state machine. Sigma is what you already know. It's an alphabet. An alphabet being a finite set of symbols. You're already familiar with that. little q0, and we'll distinguish little q is usually our states, or little s will be the states, capital Q, maybe capital S will be the set of states. So q sub 0 is the single start state, and we are only going to allow one of those. By the way, q0 has to be in the set Q. That's what this is telling us. Q0 has to be in the set Q. That makes sense, right? If you're going to start in the machine, the state has to be in the machine. And then we have F, which is a set, and it's a set of final or accepting states. Most people use F for final, but because the machine accepts strings, we also call these accepting states. F has to be a subset of Q. Cannot be it can be more than one set within the machine. So it's a subset, not an element of. And how do we figure out if a string is going to go to a final or accepting state? We have something called a transition function, lowercase delta. Delta is a transition function. Now delta hopefully is going to remind you from your calculus days, right? Delta is a small change, right? A small step forward. In this case, it's a discrete step forward from one state to another. So delta is a transition function that controls how the finite state machine transitions from state to state as the machine is processed, as the string is processed. Okay. How do these things operate? Well, initially we begin in the start state, Q0. Just like in the grammar, we started with the start string. Here we start in the start state. And we get some string U is presented to the machine. We process this string U one symbol at a time from left to right. Every time we process a symbol, we're going to transition to a new state according to the transition function. And once all the symbols in U have been processed, we're either going to be in a final state in which the machine accepts the strings, or we're in a non-final state and we reject the string. So the only way we accept is if we're done processing the string and we're in a final state at the same time. And the machine has to accept, we say, all and only strings in L. In other words, all strings in L and only strings in L. The accepted strings are in the language, the rejected strings are not. So there's a one-to-one correspondence between the language and the finite state machine. In fact, there's a one-to-one correspondence between the language, the finite state machine, and the grammar. They all provide you with the exact same information. By the way, since the finite state machine corresponds to the regular language, you now have a second way to prove that a language is regular. The first way was by looking at the rules of grammar. Now you can say, if I can create a finite state machine for this language, it is by definition a regular language. So now you have two techniques by which you can prove that a language is regular. Okay, here are the definitions. I'm going to go through about how do you draw these things, which is graphical, and hopefully will clarify any confusion that you have in the next lecture, which begins after this one.